My name is Lisa. The past 10 weeks I had the wonderful opportunity to work in Sumida Panther's Mechanical and Engineer Lab with Travis O'Donnell as my mentor, researching microbead behavior in nanochannels. So, I study particles and biomolecules in nanochannels, and this will help in the future design of lab-on-a-chip devices, pretty much making experiments run faster and more cheaper. This could also revolutionize medicine and forensic identification. With that being said, I have a picture of a glucose meter here. Currently, diabetics have to poke their finger and draw blood onto a strip in order to check their glucose levels. What understanding nanofluidics will do is it's aiming to make a chip that's able to be implanted into the diabetic, and they'd be able to check their blood glucose levels anytime, instantly. So the picture on your left is a picture of a glass chip that I work with. Typically, the chip will go from the microchannel to a nanochannel, then back to a microchannel with two reservoirs attached on the end. A better way to think about it is just pretty much a pipe that gets thinner in the middle and then bigger again on the end. And here is a picture of a glass channel and water. So typically, when you put glass in water, the glass gains a negative charge, and typically the charge would be negligible. But since we're working on the nanoscale, the charge becomes a big force. And it makes an electric double layer, which makes having a buffer with the correct pH very, very critical when flowing particles. So what I aimed to do this summer was characterize particle transport and separation in the nanochannel using electric fields and fluorescent microscopy, which helps to rapidly separate particles in nanochannels. Right here is a picture of a channel that I work with. We get them fabricated from a company, and pretty much what they are just silicon with the nanochannel etched into it. Okay, so I studied microbeads in order to understand how DNA flows in the channel, due to the fact that microbeads have similar characteristics to DNA with their charge and the size. The microbeads that I flew through the channel were 50 nanometers. So pretty much what I did was I flew the microbeads through the channel using a tris buffer set to a pH of about 8.2 using electrokinetic flow. The microbeads that I used were tagged with the fluorescent, which allowed them to shine once laser was exposed to them. And then I counted the particles that entered the nanochannel and compared that to what was in the microchannel. And right here is a channel that I worked with. Typically, they're about 320 nanometers deep in the nanochannel and about 1.1 microns deep in the microchannel with a width of about 184 microns. So in order to run my experiments, I placed the glass chip on top of the microscope and attached two electrodes in each end of the reservoirs. The electrodes were attached to a high voltage supply. Typically, I worked with about 200 kilovolts. So once I shined the laser onto the channel, fluorescence was exposed out or came out into the microscope and onto the camera, where I recorded them on the computer and observed the particle flow. So the first thing that I looked at when trying to understand more about nanofluidics was the flow rate of fluids in the nanochannel. And as one would assume, the flow in the nanochannel was more faster than the flow in the microchannel. And right here is just a bright field image of the view of the channel that I used. And here's a fluorescent image of the channel with particles flowing through it. Okay, so another thing that I looked at during my course of research was how the particles behaved in the channel without voltage. And one issue that I ran into was the fact that the particles in the nanochannel tended to stick to the wall due to electrostatic forces, versus in the microchannel. As you can see here, the particles are more dispersed throughout the channel. So I got another channel, and I ran some more tests. And the issue with this channel that came across was that at the interphase, as you can see, the interphase is a lot more fluorescent versus the rest of the channel. The particles in the flow from micro to nano channel, a lot of the particles got stuck in the interphase, making the particle count a little bit off. As you can see, there are more particles in the microchannel versus that of the nanochannel. So in conclusion, I with my issues that I ran into this summer were the fact that the microbeads, once they enter the nanochannel, due to van der Waals forces and electrostatic forces, the particles would stick to the wall versus flowing through, and the interphase, the channels that I worked with, would often trap the particles. For future work, something that I can do is get a different ionic strength buffer, which would help particles not to stick to the walls. I'd like to be able to count the particles once they go through and observe the effect that the interface has on the particle flow. And in conclusion, I'd like to thank Sumita Pinithar for allowing me to work in her lab, Travis for being such a great mentor, everyone in the Pinithar lab that allowed me to ask them lots and lots of questions, EUREKA for providing me with this opportunity, and EUREKA for funding me this summer.
Questions for Lisa?
So, is the interface from going from the microchannel to the nanochannel, is it like a gradual decrease to the nanochannel, or is it just
It's
right
just
angle?
an angle. Yeah, right angle. It's not gradual. It just goes from micro straight to nano.
You think maybe making it a gradual one would sort of reduce the amount of particles getting stuck?
I honestly do think that, actually, but that's something that we'd have to talk about with the company that fabricates them for us.
Why exactly does it have to go through the nanochannel?
Because we know a lot about microfluidics right now, so we're using what we know about microfluidics and using that to gain a better understanding in the nanochannels of nanofluidics. So we compare it to what we know to what we don't know. Yes.
You said glass is electrostatically charged, so could you use particles that are not so sensitive to the polarity of the charges?
That's why we use a buffer in order to make the charge a little bit more stable, but I still encountered problems with some of the channels. Yes.
So did you alter the concentration of your microbeads that you were running through your channels, and do you think maybe changing the concentration might change how the beads get trapped or don't get trapped?
Yeah, I actually did. I tried, with one dilution that I had, there were too many particles, and I tried diluting it again, and then you couldn't see anything. So I pretty much went with the more concentrated solution.
Any questions? Okay, great. Thank you.